Okay, so welcome back to the week 6 of the problem solving session for the Introduction to Fluid Mechanics course, and we'll wait for 2 more minutes uh, to let other students also join. If not, then we will go on with our regular agenda. And just to make sure, am I audible properly?
Yeah.
Okay, thank you. So uh, we'll wait for 1 more minute and then we can start the session. Okay, then I believe we can start the session. So in this week's session, we'll be mainly dealing with three topics, and which is which is actually in continuation with the previous week's topics of fluid visualization and introduction to fluid kinematics. So this week's topics include three main subtopics, which are deformation of fluid elements, which we already dealt last week. Last week we dealt with the linear deformation of fluid elements, and this week so we'll be dealing with the angular deformation of fluid elements in depth. Okay, then we will be dealing with a very important concept, that is the concept of stream function, and its used in solving fluid flow problems and its applications. And finally we will be discussing about velocity potential and circulation. I have not I have not mentioned as a separate topic because it comes included with the concept of deformation of fluid elements, specifically the vorticity vector. Okay, and I hope the students have watched the lectures by Professor Chakraborty. And as per our regular agenda, today we will be briefly revisiting the concepts taught by Professor Chakraborty in the lectures. Obviously, I will not go to the detailed derivation of each and every topic, but we try to go through a brief overview of the concepts that were discussed in the lectures. Then we will try to solve some similar problems that were discussed by Professor Chakraborty in the lectures, and then we will be dealing with some problems that will help you to solve the assignment problems for this week's assignment. Okay, so I hope the agenda for today's session is clear, and let's then begin with today's session. Okay, so as mentioned in the last week's session, we discussed about linear deformation. Okay, so linear deformation basically implies the elongation or contraction along a particular coordinate direction. Okay, since in this notation we are dealing with a Cartesian coordinate system, so we are essentially mentioning that the fluid element would elongate or contract along a particular coordinate along a particular Cartesian coordinate direction. Okay, say along the x, y, or z axis, which are denoted by epsilon x dot, which is equal to dou u by dou x, epsilon y dot, which is equal to dou v by dou y, and epsilon z dot, which is equal to dou w by dou z. And by dou I am referring to the partial derivative of respect to a particular coordinate direction. Okay, and similarly the sum of these linear deformations along the three coordinate direction would give us the rate of change of volumetric strain. Okay, which is basically the divergence of the velocity field. Okay, so it is just previous week's discussion, because it comes under the deformation of field elements. I am revisited it, but it's not what we will be dealing with in this week's session. Okay, so our main focus would be primarily on the angular deformation of fluid elements. Okay, so this diagram was discussed by Professor Chakraborty in his lectures, so I'll briefly go through it, but just for your recapitulation, I will give you few minutes to go through a diagram, and then we'll discuss a bit about the derivation, and then we can go ahead to learn the concept. Okay, I hope that's clear. So I'll give you a few minutes, just 1 minute, say 30 seconds or 1 minute, to go through a diagram. Let me zoom it a bit so that you can recapitulate what was discussed in the class and then go ahead with the derivations. Okay, so of course if you have any doubt, you can stop me at any moment. I will try to clear it, and if then also it's not clear, you can just revisit the lectures by Professor Chakraborty. Okay. Okay, I think you were able to go through the diagram, so I hope the diagram was clear. In this diagram, we are basically dealing with a particular fluid element given by A, B, C, D. Like the fluid element can be of any shape, so just for our ease of our understanding and deriving the mathematical terminologies or equations, we are considering the fluid element to be of a rectangular shape, okay, whose length along the x-axis and along the x direction and the y direction are given by delta x and delta y. Okay, it's a fluid element, so it's a very small length, so we are representing it by delta x and delta y. Okay, so let us assume that after some time, say delta t, the fluid element has traversed a particular displacement, say a dash, that is the point A has traversed a distance of a dash, and the fluid element has deformed to this current form, okay, to this current shape. Again, this deformation can be of any shape and can be random, but just for the ease of our understanding and deriving the mathematical equations, we are considering a generic deformation form of deformation, so that we could capture the flow physics properly. Okay, so just for our ease of understanding, we are considering this simple deformation deformed shape. Okay, so initially the fluid element was rectangular, now it has turned to a rhombus shaped element. So the point A has traversed the distance, say r, and has reached point a new location A dash, and the other coordinates of the fluid elements have also changed to B dash, C dash, and D dash respectively. Okay, and specifically we are interested in these two lines of the fluid elements, that is A dash B dash and A dash D dash. Okay, so that we could capture the angular displacement of the line elements. Okay, so if the fluid element was initially at point A, then the distance traveled by the point A to A dash along the y-axis is given by v delta t. Okay, say that we have allowed the fluid element to travel for a small time delta t, and the velocity at point A was given by u and v. Then the displacement of point A to A dash along the y direction is given by v delta t. Okay, and if along the x-axis, it will simply be u delta t. Okay, but since we are interested in the displacement along the y direction, so then this displacement, say b e dash, is given by v delta t. Okay, you can stop at any moment, like if you have any doubt regarding the diagram or the mathematical interpretation of the derivations, you can stop me. Otherwise, you can just, if you have any doubt later also, you can just go through the lectures by Professor Chakraborty or put your doubts in the discussion forum. Okay, so I hope it's clear. Okay, then the distance b e dash, say, is given by, or a e dash, even, in fact that's fine, is given by v delta t. Okay, now we are again interested to know how the point B has shifted in this course of time. Okay, in the course of time delta t. Okay, then if the velocity at point A is given by uv, then the velocity at point B, say it would be u plus delta u and v plus delta v. Okay, say it is v plus delta v. Then v at B is v plus delta v. Okay, or more precisely, you can say v plus some v at a distance of x plus delta x. Okay, because this, if this is x, then point B would be at a distance of x plus delta x, right? So we can just say that velocity at point B is velocity at point x plus delta x, and then velocity at point B could be evaluated using the Taylor series expansion, right? Taylor series expansion. Right? Then the velocity at point B would be given by this expression. Okay, this is v plus dou v by dou x delta x plus v by dou square v by dou x square delta x square by 2, and this expansion will go on, but let us say that we are interested only to the first derivative. Okay, then we can just consider rest of the terms as higher order terms. That's fine. Then the the displacement, then the distance b e dash. Okay, this distance b e dash would basically be b b dash minus b dash, b e dash, right, would be equal to b dash e dash, right? Because we are interested to know about the angle alpha, then we can, if we consider this as a right angle triangle, then if we know these two distances, say b dash e dash and a dash e dash, then we can easily find the angle alpha, right? So I hope it's clear. Then this distance b dash e dash is given by b dash minus b e dash, where b dash will be given by this expression. Then just subtract v delta t from this length to get b dash e dash is equal to dou v by dou x delta t plus some higher order terms. Okay, similarly the displacement a e dash, okay, because since the fluid is traveling has deformed after some time delta t, then the length along the x direction has also changed. Okay, it will also change, but let's say it won't change that significantly, because there is no critical angular displacement along the x direction, say, because we are only primarily concerned with these two angular displacements. So there is no critical angular displacement along the x direction, say. Then we can say that the displacement along the x direction would be, say, delta x, the initial length, plus some higher order terms. Okay, plus some higher order terms, which are again which can consider to be negligible. Okay, say see, these are considered to be negligible. Why? Because the very length scale that we are dealing with is itself very small. Okay, delta x, like if we consider the size of the fluid element to be very small, then if we are considering a fluid element which has its initial length as delta x, then the change in the length of the fluid element because of its movement along the movement and deformation in the flow would also be very small. Okay, so we can effectively consider those small changes in the length, and that's why we are considering as some higher order terms, which can effectively be neglected for the ease of our calculations. Okay, and that's why if we now know a dash e dash and b dash e dash, then the angle the tan of the angle delta alpha would be given by tan delta alpha would be b dash e dash by a dash e dash, right? It's quite simple. Then we just divide this from this to get tan delta alpha is equal to dou v by dou x delta t, and again plus some higher order terms. Okay, now if we consider this approximation, then this angle delta alpha is again very small. Okay, it's very small. Then we can effectively consider tan delta alpha to be equal to delta alpha. Okay, to be equivalent to delta alpha. Again, for the limit of delta t tends to 0, again this is also very important. Why, I will let you know in a moment. But let's say we are considering the angular displacement of this fluid element for the limit delta t tends to 0. Then for the limit delta t tends to 0, delta alpha by delta t would be equal to dou v by dou x which comes from this, that is equal to alpha dot, okay, or rate of change of the angle alpha. Okay, now why to consider this limit delta t tends to 0? Okay, see, in the very first class, while we were defining fluid, we told that the major difference between a fluid and a solid is that under the application of a certain force, the fluid will continue to deform will continue to deform will continue to deform infinitely for as long as the force is being applied, right? It will undergo continuous deformation under the application of some certain force. Okay, but a solid would try to resist the application of resist that application of the external force on it by applying some resisting force, which results in the generation of stress in the solids, right? That we usually discuss in the solid mechanics, like how stress is generated, right? Because once the force is being applied on the solid, the solid tries to retract back to its initial position, and this tendency of the solid to get back to its original initial shape results in the generation of internal stress, which is or internal resisting force, which is termed as stress, right? Internal resisting force per unit area, which is termed as stress. But in the case of fluid, there is no such internal resistance to the applied force, right? It will go on to deform continuously if the force is being applied continuously, right? And that's why, to capture the essence of these angular displacements for a small period of time, that's why we are considering our time delta t to be very, very small. Because if delta t is very, very large, then this fluid element will go on to deform continuously, and it will be very difficult to capture the angular deformation of the fluid element. Okay, and that's why we consider this time delta t to be very, very small, and that's why also in case of fluid mechanics, it is actually the rate of strain or rate of strain rather than the total strain that is a more important physical parameter. Okay, because in the case of solids, it's actually if we consider the Hooke's law, it tells us that the net stress is directly proportional to the net stress is directly proportional to the net strain in the body up till the elastic limit, right? But in the case of fluid, if we consider a Newtonian fluid, say, then from Newton's law of viscosity, tau is equal to mu epsilon, if we consider a stress tensor, tau ij is equal to 2 mu eij, and this term eij in essence is actually the rate of strain rather than the total strain rate or total strain. Okay, it's actually the rate of strain or the strain rate. Okay, so I hope this was clear. The whole derivation of the angular deformation in fluid elements, I hope this concept was clear. And similarly, if we apply the similar calculations along the for the angle beta, for this angle beta, we will get that the rate of change of displacement with respect to the y-axis, that is beta dash, is equal to dou u by dou y. Okay, so I hope it was clear up till this point, and again, if you have any doubt, you can just revisit the lectures, or if you have any doubt, you can ask me now as well, but I hope it was clear. Okay, so let's move ahead then. Okay, so now we got that alpha dot, write it properly, alpha dot is equal to dou v by dou x, and beta dot is equal to dou u by dou y. Okay, so we are just considering a 2D case. So we have two angular displacements or rate of angular displacements, that is alpha dot is equal to dou v by dou x, and beta dot is equal to dou u by dou y. Okay, then the rate of strain or angular deformation is given by the rate of change of angle between the two line elements in the fluid which were originally perpendicular to each other. I hope you are able to correlate this definition with the derivation that we just did. If you just go back to our diagram, we considered initially a rectangular element, and we considered two line elements which are initially perpendicular to each other, right? And then we found out how these line elements or the rate at which these line elements deform with respect to their original positions, and then found the rate of change of angular displacements of these line elements. Okay, so by definition we got that the rate of change of angle between the two line elements in the fluid, the rate of angular deformation is actually given by the rate of change of angle between the two line elements in the fluid which were originally perpendicular to each other. Okay, I hope the definition is clear. Now if we try to derive it or write it mathematically, we get that initially, since the angle between the two line elements, say if I draw it like this, the initial angle between the two line elements were 90 degree, right? So pi by 2, and after deforming, let me use different color, say after deforming, the angle between the two line elements would be now pi by 2 minus alpha minus beta, right? I hope this is clear. It's pretty simple. Then we again take the limit delta t tends to 0, right? Why we take delta t tends to 0, I guess I have talked about it extensively, so I don't have to repeat it. So once we do this evaluation, we get that the rate of angular deformation is given by alpha dot plus beta dot, okay, or the sum of the rate of angular deformation of the two line elements, okay, which will basically be dou v by dou x plus dou u by dou y. And since we are considering along the x, only along the fluid element along the xy plane, so this rate of change of angular deformation along the xy plane is given by epsilon dot xy. Okay, similarly epsilon dot yz is given by dou w by dou y plus dou u by dou z, and epsilon dot zx is given by dou u by dou z plus dou w by dou x. Okay, this final equation or the final expression for the epsilon xy dot is given by this, and it has to be derived by after an extensive mathematical derivation, right? Has to be, and it, what I basically mean to say is we derive this final expression after a extensive mathematical say calculations or derivations. After that only we reach to this conclusion, and which itself has a very deep physical meaning. Okay, but again, since math itself has pattern which a pattern that is being followed, that has an inherent pattern that is followed in different phenomenons. Okay, or I can say that the math has a strange nature of having inherent patterns that once if we can capture it, it is very easy to understand or at least formulate the physical phenomena. Okay, so what I mean to say is that, see, if you look in this expression epsilon dot xy, you can see clearly that there are two Cartesian coordinate directions, right, x and y, which has corresponding velocity components as u and v. Okay, u along the x direction and y along the and v along the y direction, right? So you can clearly see that the rate of change of angular deformation along the xy plane is given by dou v by dou x plus dou u by dou y. Okay, or basically just the velocity components for the two Cartesian coordinate directions are interchanged. For x instead of u I have now v, and for y instead of v I have u. Only the velocity components have been interchanged. So similarly, if you look into epsilon yz, you can follow the same pattern in this expression as well to get that epsilon dot yz is dou by dou y. Now we just interchange v instead of w to get dou w by dou y plus dou by dou z again interchange w instead of v to get dou v by dou z. So epsilon dot yz is equal to dou w by dou y plus dou v by dou z. Similarly, we have epsilon dot zx is equal to dou u by dou z plus dou w by dou x. Okay. I hope it was clear. And again, instead of since these expressions are valid only for a Cartesian coordinate system, that is an xyz coordinate system, we try to generalize this expression in form of a tensor. Okay, specifically a second order tensor, where we present epsilon dot ij, where I and j denotes the two coordinates, two perpendicular coordinates with respect to which we are finding the rate of change of angular deformation. To get that, epsilon dot ij is equal to dou ui by dou xj plus dou uj plus dou xi. Okay, and for a Cartesian coordinate system, this I and j would vary as 1, 2, 3, or specifically would imply the x, y, and z coordinates. Okay, then if you go to spherical coordinates, that would be r, theta, and phi. For cylindrical coordinates, it would be r, theta, and z. Okay, so this expression is these expressions are only valid for Cartesian coordinate system, and this expression is valid for any coordinate system. Okay, we just need to change the or use the respective form of the derivatives to get the rate of change of angular deformations. Okay, so I hope it was clear till now. And again, we'll for the sake of saving time, I don't think I will again go on extensively to discuss the rest of the derivations again, because I just wanted to discuss about the angular deformation in depth, because this lays a platform for the rest of the topics that we are going to discuss today. Okay, so once you know the very concept of angular deformation, you'll be easily able to grasp the following concept that we are going to discuss. So that's why I wanted to discuss about it in depth. Okay, so again, angular velocity is simply given by the arithmetic mean of the angular velocities of the two line elements which are originally perpendicular to each other. Okay, so if we go back to the diagram, let me just draw it again. So initially the fluid element was of this shape, and then after some time the fluid element has deformed. Okay, I don't think I will be able to draw the entire diagram, just say like this. Okay, and then if we consider, again, there is a concept of sign convention. Say if I consider the rotation along the counterclockwise direction as positive, okay, and rotation along the clockwise direction as negative. But this is just my notation, okay, and that I like to follow, and I guess same has been followed by Professor Chakraborty, but you can always use the opposite notation. It won't make any difference. Just the sign in front of your answer would change, which you need to specify by saying that I have chosen it to be positive along the clockwise direction and negative to be in the counterclockwise direction. Okay, you just need to mention that. But the general sign convention that has been used in this course, and which I personally like to use, is that the counterclockwise direction I take it to be the positive sense, and the clockwise direction I like it to be the negative sense. Okay, why? Because this is a general trend that is that has been used by many authors and in many research publications as well. Okay, just to fit in with the general trend of notation, I like to use such conventions. Again, similar sign convention can be interpreted in thermodynamics as well, or direction of heat transfer, that many people use in a different way, but all are acceptable. You just need to know the concept properly. So that's why if we consider it to be positive along the clockwise direction, then alpha dot will be positive, and if we consider it to be negative along the clockwise direction, then beta dot would be negative. Okay, if I mispronounced it, I was saying that if alpha dot is along the counterclockwise direction, then alpha dot would be positive, and if beta dot is along the clockwise direction, then beta dot would be negative. And as I said, angular velocity is the arithmetic mean of the angular velocities. Then we need to take the sign conventions as well while we add up these angular velocities. Then omega xy or omega z, say I will let you know why I'm saying omega z, is given by half of alpha dot plus minus of beta dot, because it is in an opposite sense. Then we get that omega z is equal to half dou u by dou x minus dou u by dou y. Now you know why I discussed in depth how these derivations were obtained. So I'm not going to discuss how alpha dot is equal to dou u by dou x and how beta dot is equal to dou u by dou y. Okay. Similarly, as the convention as we try to write the angular deformation in terms of a second order tensor, we again write this angular velocity as a second order tensor to write as omega ij is equal to half dou u j by dou xi minus dou ui by dou xj. Okay, I hope the equations are clear. If there is any doubt, you can ask. There is no issue. Okay. Again, these two respective tensors, that is the angular velocity and the angular deformation tensors, have some interesting properties. That the angular velocity tensor is actually a skew symmetric tensor. That is omega ij is equal to minus omega ji. Like if you interchange the if you take a transpose of this tensor, if it is a 3D, if you are considering 3D, then it will be a 3 cross 3 matrix. Then if you take a transfer of that matrix, then it will be negative of your initial matrix. So omega, the angular velocity tensor is a skew symmetric tensor. Okay, or matrix is just a generic name I have given to it. Okay, and similarly, the shear deformation or the angular deformation tensor is a symmetric tensor. It is E dot ij is equal to E dot ji. Basically, if you take a transpose of this matrix formed, say a 2 cos 2 matrix for a 2D flow and 3 cos 3 matrix for a 3D flow, then the transfer of that matrix would be the same as the initial matrix that we are considering. Okay, so again, crucial properties, that angular deformation tensor is a symmetric tensor and the angular velocity tensor is a skew symmetric tensor. Okay, so I hope you get the difference between the symmetric and the skew symmetric part. Okay, so is it fine till now? Like, are you able to understand what we discussed till now?
Yeah, can continue.
Okay, thank you. So I think since it is clear till now, so let me just move ahead. And again, so this was a special case discussed by Professor Chakraborty in the class, that he mentioned that angular velocity in its essence, though it gives an idea or sense of rotation, okay, rotation along a particular direction, say along the clockwise or the counterclockwise direction, in essence angular velocity is itself what it means. It is referring to rotation. Okay, that if we try to compare it to solid mechanics case, right, when we are considering angular velocity, angular acceleration, we are basically dealing with rotating elements, right. But in the case of fluid, it's not that very straightforward, as rightly pointed out by Professor Chakraborty, because if we look back, look into this diagram, you can see that even though there is a rotation, say if we consider this line element, then there is a rotation along the counterclockwise direction. That's fine. Again, if we consider this line element, there is a clockwise rotation. Again, that's fine. But the effective essence of the proper rotation of the fluid elements is not being captured in this diagram, because in its very definition, this fluid element, rather than rotating, is actually deforming, right. It's not physically, we cannot say that fluid element is rotating, but still this physical phenomenon has a angular velocity which is defined by this expression. Okay, it is the mean of the rate of change of angular displacements of the two line elements which were initially perpendicular to each other, right. So even though the very physics of rotation is not explicitly being observed in this picture or in this discussion, yet there is a definition or a terminology of angular velocity involved in this phenomenon. Okay, so that is what something interesting in the case of fluids, as pointed out by Professor Chakraborty. But again, this phenomenon can also have a special case, right? If we consider a case where alpha dot, let me just write it, alpha dot is equal to minus beta dot, or vice versa. Okay, so it will basically mean that this line element, instead of having a displacement along this along the clockwise direction, it would have a equal angular displacement along the clockwise direction. Let me use a different color so that you can understand it. So, and this angle would be equal to, or rate of change of angle would be equal to beta dot. Then if we just then draw the complete the fluid element, okay, sorry, just extend it. Okay, so now you can see that there is a proper explicit rotation of the fluid element for this particular case or this specific case. Okay, now you can clearly see the fluid element is rotating about the origin. Say if that point is 0 0, just for the sake of understanding, I'm saying if that point is 0 0, then you can say that the fluid element is rotating about the origin. Okay, similarly, if beta dash is equal to minus alpha dash, it will rotate in the counterclockwise direction. Okay, then you can say that this case of the fluid element having explicit rotation is a special case of the definition that is given to the angular velocity for a fluid element. Okay, I hope it was clear. Like, even though there is no proper rotation, no explicit rotation on the fluid element, yet the angular velocity is defined for a fluid element. And the essence of rotation that we try to understand in the or that we observe in the case of solids is actually a special case or rigid body rotation that I am trying to mention. This is what I am explicitly trying to mention, that the case of rigid body motion or rigid body rotation is actually a special case of angular velocity in the case of fluids, okay, or fluid elements. Okay, so I hope this was clear. It's a very interesting concept. Like sometimes it may be also be asked in the interviews, like even if the fluid element is not rotating, how it can have angular velocity. Okay, it's just a definition. It is used to understand the deformation in fluid elements, and the rigid body rotation or the rotation in solids that we observe is actually a special case in the case of fluids. Okay. Again, there is some more mathematical manipulations. That is, the velocity gradient can actually be written as a sum of a symmetric and a skew symmetric matrix. Okay, so, and the symmetric matrix is essentially the rate of angular deformation matrix, and skew symmetric matrix is the angular velocity tensor or angular velocity matrix. Okay, it's just simple. These two terms will add up to get for you to get this term, and these two terms will cancel out because of the minus sign. Okay, it's just a mathematical manipulation to show that how the velocity gradient can be represented as a sum of a symmetric and a skew symmetric matrix. Okay, that's fine. Again, it's just a a conceptual add-on to your knowledge pool, like something that is good to know, but it's not bad if you don't know as well. But it's a good way to understand how the concept of the sum of symmetric and skew symmetric matrix representing a certain entity comes into picture in the case of fluid mechanics as well. So that's what I wanted to point out, but that's fine. Okay, so while we are dealing with angular velocity, again, you can easily understand that since if you're talking about angular velocity, vorticity, we cannot disregard vorticity. They are basically the same, or in fact they are exactly the same, just differing by a scale factor of 2. Okay, So I'll let you know, I'll show you how. So vorticity in the case of fluid mechanics is defined as the cross product of the Nebula operator with the velocity field, okay, or the curl of the velocity field, okay, which is now, if we take those, if we take down the expression, is given by this, okay, where all these terms explicitly denote the magnitude of the vorticity along the particular coordinate direction, okay. So omega x is given by dou wy minus dou v, dou w by dou y minus dou v by dou z. Then omega y is given by dou w by dou x minus dou u by dou z, and omega z is given by dou v by dou x minus dou u by dou y, okay. And you may wonder like why I have written these terms as well, okay. See, omega z would include velocity components that are perpendicular to it, okay. Similarly, omega y would include velocity components that is perpendicular to it, and omega x will include velocity components that are perpendicular to it. Why? Because since we are dealing with cross product, the final vector would always point in a direction perpendicular to the plane of consideration, okay, the plane where the evaluation has been taken. Since we are dealing with since we are dealing with derivatives along the y and z direction, the angular velocity would point towards the net angular velocity, or the component would point towards the x direction, right? Similarly for the other two elements as well, okay. Since the velocity components that we are dealing with are along the x, along the y and x direction, then the resultant cross product would always have its component perpendicular to these two velocities, which is essentially the z axis or the z component, okay. And you can see that once you do a calculation, you get that the vorticity vector is actually twice the angular velocity vector, okay. And I don't think I need to define like why they are related, because they are exactly the same thing. They are just differing by a scale factor of 2. And if you try to again correlate or have a very simple definition of their relation, you can just say that a fluid with higher angular velocity would imply higher vorticity in the flow field, and vice versa, okay. So I hope it's clear. It's actually very good to know the flow physics and how they're related, but for today's session, I think the more important thing would be the mathematical formulas that we are dealing with, okay. So it will be good if you try to recall what are the formulas for vorticity or angular velocity, because sometimes it may happen that even ignoring the scale factor of half may result in wrong answers, right? Because the angular velocity is actually the half of the vorticity, right? If you forget this factor of 2, you may get wrong answer, okay. So it's important to recall the formulas, and specifically we'll see how we are dealing with these formulas to solve problems in this in today's problem solving session, okay. So now we are we will be dealing with a very important concept, a very crucial concept in the case of fluid mechanics, okay. And that is specifically the stream function. And stream function, you can essentially consider it to be as a tool that is used to simplify 2D incompressible flows, okay. Why? See, stream function by its very definition, or by its very essence, is only defined for 2D incompressible flows or axisymmetric incompressible flows. Axisymmetry itself tells us that the velocity has no dependence along the along the angular direction. So that is there is the derivative of the velocity field along the angular direction would be 0, okay. So it essentially implies axisymmetry. So in that case also the stream function is very much applicable, but in general we consider that stream function is applicable and is valid for 2D incompressible flows. Okay, so if we consider a 2D incompressible flow, the continuity equation will be given by dou v by dou x plus dou v by dou y equal to 0. Okay, now if we define a function who represents the velocity field as u is equal to dou psi by dou y and v is equal to minus dou psi by dou x, then where psi is the stream function, okay, where psi is the stream function, where psi would be a function of x and y. Okay, then if we substitute this expression back in the continuity equation, you will see that it satisfies the continuity equation automatically. How? It's very simple. U is dou psi by dou y and v is equal to minus dou psi by dou x. Just substitute the expression for u and v in this expression to get, you will get that dou square psi by dou x dou y minus dou square psi dou y by dou x is equal to 0. Of course, if psi is a smooth function. Okay, that basically allows us to interchange the order of derivative. Okay, so in that case you can clearly see that the stream function automatically satisfies the continuity equation. Okay, now again if we consider the total derivative of psi, and this I'm just doing it to show you how the stream function is has a certain relation with the streamlines as well, but again they are not exactly the same thing. Okay, so why they are not the same thing, again I will tell you why. So since psi is a function of x and y or x and z or y and z, it just needs to be 2D. Okay, so since it's a 2D function, so if we consider a total derivative of psi, okay, which is denoted by d psi, then d psi would be given by dou psi by dou x dx plus dou psi by dou y dy. It's the formal definition of total derivatives, so I don't think I need to show you how we can approach it, but it's just the formal definition of a total derivative. Okay, so since we know dou psi by dou x is equal to minus v and dou psi by dou y is equal to u, we substitute that in this expression to get that d psi is equal to minus v dx plus u dy. Okay, now if d psi is equal to 0, or basically if psi is equal to constant, then we get v dx minus u dy is equal to 0, or dx by du is equal to dy by v, dx by u is equal to dy by v, which is basically the equation of streamline for two velocity components, or in case of 3D it had dz by w. Okay, but from here you can clearly see that for a 2D flow the stream functions will essentially constant stream functions having constant values with constant values give the streamline of the flow. Okay, in the case of 2D flows, but the crucial difference between streamline and stream function is that stream function is only defined for 2D incompressible flows. Okay, but streamline is valid for all types of flows. Okay, it's not limited to 2D flows, but it's defined or valid for 3D flows, 2D flows, 1D flows, all types of flows. Okay, but stream functions are only valid for 2D incompressible flows. Okay, so that's the basic difference, and from this expression it basically tells us that stream functions having constant values gives the streamlines of the flow. Okay, so let us try to solve one problem regarding stream functions. Now that will help us to understand the concepts properly, so that's fine. Okay, so consider this question that u is equal where the velocity components are given by u, v and w, where u is equal to 0, v is equal to minus y cube minus 4z. Sorry if it is unclear. So, and w is equal to 3y square z. Okay, since we are discussing a problem, you can stop me at any time to ask if you have any doubt, okay, regarding derivations or the terminologies that I have discussed. So you can stop at any time. Okay, So the first question is, what type of flow does this velocity field show, or velocity field implies? 1D, 2D or 3D? So again, just by looking at the velocity field, you can tell that it shows a 2D velocity field because it has only two velocity components, and the velocity component along the x direction is 0, so that's why it's a 2D flow. Second question is whether the flow is compressible or incompressible, and in order to do that, we know that for a flow to be incompressible, we need to have the divergence of the velocity field to be 0, right? Then we just find the divergence of the velocity field. Just in this case it is 2D, so it will only have, and with v and w velocity components, so the divergence of the velocity field will be given by dou v by dou y plus dou w by dou z. Then if we take the partial derivative of v with respect to y, we will get minus 3y square, and dou w by dou z we will get 3y square. If we add it, we get that dou v by dou y plus dou w by dou z equal to 0. And since the flow is 2D and incompressible, the stream function of this flow would be defined, right? This flow would be can be defined using stream functions. Okay. So again, in this case, again since the stream functions are defined, we can write v is equal to dou psi by dou z, and w is equal to minus dou psi by dou y. Okay. Again, there is no restriction in putting the minus sign. You can in fact even write v is equal to minus dou psi by dou z, and w is equal to dou psi by dou y. But you need to keep minus sign in one of the velocity components so that the continuity equation is satisfied. Okay. And just check the derivative. If it is with respect to w, then we will have a derivative with respect to y, and if it is v, we will have a derivative with respect to z. Okay. Just need to check the derivatives and the negative sign. Okay. Otherwise, whichever the velocity field your velocity component you're considering, you can keep the minus sign anywhere. Okay, that's fine. So from this expression, we get that v is equal to minus y cube 4z is equal to dou psi by dou z, and w is equal to 3y square z is equal to minus dou psi by dou y. To find psi, we just need to integrate this expression to get that psi is equal to y cube z minus 2z square plus some function of y, because since this partial derivative, we have some function of y, and plus some constant if you want to consider. Okay, say some constant c1. Then from this velocity component, we get that w is equal to 3y square z is equal to minus dou psi by dou y. If we integrate it partially, we get that psi is equal to minus y cube z plus some function of z plus some constant c2. Okay. Now if we compare both these expressions, this and this, we can clearly see that the function y in this case is itself y cube z, so it remains, and some function of z is itself minus 2z square. Okay, so if we compare both these expressions, we get that psi of yz is equal to minus y cube z minus 2z square plus c plus some constant. Okay, again, if we want to define and this constant would itself give us the different streamlines. Okay, so streamlines of the flow. Okay, so if we consider psi 0 0 to be 0, we are just considering a generic case where psi 0 0 is equal to 0, then psi yz is equal to minus y cube z minus 2z square. Okay, so is this derivation clear? How we found psi? Is it clear?
Yes, let's proceed.
Okay, thank you. So because we were dealing with similar problem in the assignment, I wanted that it to be clear, so thank you. Okay, so I think this is this circulation and then angular velocity are two final topics that we'll be discussing for today's session, so that's fine. Okay, so circulation itself, again, as I told, is something that we cannot separate from the concepts of the deformation of fluid elements or the angular velocity, because it itself inherently captures the concepts of vorticity in it. Okay, how we'll see now. Okay, say that we are considering a fluid element having a certain boundary. Okay, and let V be the velocity vector across this fluid element, and let dl be the elemental length of the boundary of this fluid element or flow domain. Let us not limit ourselves to fluid element. Let us say it is a flow domain where this V vector denotes the velocity field along a particular direction, and dl denotes the elemental length of this flow domain. Okay, then the line integral or closed line integral of this velocity vector or the dot product of the velocity vector and this particular I'm sorry, because since we are already considering line integral, then it will inherently come into picture. So if we consider a closed line integral of the velocity field, it represents the circulation of the flow field for this particular domain. Okay, so this is what circulation is defined as. Okay, the cycling integral of V dot dl in a particular flow domain is known as the circulation of the flow field. Okay, circulation of the given flow field. Okay, now if we apply in this expression, if we apply the Stokes theorem of converting line integrals to surface integrals, I need to denote it as double integral. Okay, so by Stokes theorem, we can convert this line integral into surface integral, right? Where surface would essentially be the net area bounded by this closed curve or bounded by this boundary of this flow domain. Okay, so from Stokes theorem we can write this line integral in this form. That is the curl of the velocity field times the the surface integral of the curl of the velocity field over this closed surface that is bounded by the boundary of the flow domain. Okay, so which will again be equal to the net circulation. Okay, so you can clearly see that how the very definition of circulation itself has the concept of vorticity embedded in it. Because if you can clearly see here, like if the vorticity of the flow field is 0, the net circulation will also be equal to 0, right? What I am trying to say is, if the curl of the velocity field is equal to 0, it will essentially mean that the circulation of the flow field is also 0. Okay, this is a very crucial concept, because sometimes people, since the very first definition that the students usually deal is actually line integral, which does not capture the essence of vorticity in it, so people forget that vorticity and circulation are actually very closely related. So that's why I just wanted to point this out. And actually, if somebody is very strong, has a very strong mathematical base, they will clearly see this relation and point out themselves that how circulation and vorticity are related. Okay, so for the and again, so this surface integral again can be considered to be as the product of vorticity and the area vector. So you can consider, or magnitude wise you can consider it to be vorticity times area is equal to circulation. Okay, so sometimes in some questions, in some problems, it may happen that the surface area and the vorticity are explicitly given, and they are asked you to find out the circulation. So in those cases, if there is no need of applying the line integral or the surface integral, and since the circulations over a particular defined shape is already given, then you can directly apply the formula of the curl of the velocity the vorticity times the area of the particular flow domain which has a defined shape, say, is the circulation. So we can write that vorticity is equal to circulation times the area. Okay, and from this expression also you can tell that if vorticity is equal to 0, it basically implies circulation is also equal to 0. Okay, obviously for a finite area. right? Okay, so let us consider this small example. Uh, so here it is given that consider the velocity components that that is given by v theta is equal to omega r and vr is equal to 0. So it basically tells us that the angular velocity component is omega r and radial velocity component is 0. So it's basically a 2D flow, and from its definition it actually represents a forced vortex. Why? Because the angular velocity component is proportional to r, and if it was proportional to inverse of r, it would basically represent a free vortex, which we will again see. Okay, so and the flow domain is given by this particular shape, a particular area of a sector of a circle. So this, the area of interest in this case is given by this red line element given by a, b, c, d. Okay, so then we consider to find out the circulation, let's consider the different line elements separately. It is AB, BC, CD and DA. Okay, then let us consider that the radial distance from the center of the circle to point A is r, and the length of this element is say dr, and the angle that is enclosed by this sector is d theta. Okay, then the arc length AB would be given by rd theta, right? If this is the radial distance and d theta is the angle enclosed by this sector, then the arc length AB is given by rd theta, right? And if we consider the say the length or depth along the say okay, sorry, since we are only considering the length element, then there is no need to consider the area. So the total length that is enclosed by the curve AB is rd theta, right? And the velocity component is omega r, because the radial velocity component along the flow, along this flow domain is omega r. So v dot dl along AB is omega r into rd theta. Okay, so I hope it's clear. And again there is a minus sign, because if we consider that we are considering the circulation along a particular direction, because this evaluation has to be done considering in a particular sense, okay, along a particular sense only. Either you consider all your calculations along the clockwise direction or the anti-clockwise direction that is being done here. So since we are doing this evaluation along the counterclockwise direction, and the velocity component we are considering here is along the let me just wait. Okay, so yes, so since the velocity component here, if we consider it to be along the curve, is towards the clockwise direction, that's why we have the net product of v dot dl as minus omega r into rd theta. Okay, similarly for the line element BC, the interesting part is again that here, since in along this line element the product of again this line element would be encountering two velocity components, that is the angular component and the radial component. Okay, see, but since we are considering a dot product and the velocity component perpendicular to it, v theta, even though it has a finite magnitude, but since it is perpendicular to this this particular line element, that's why the net product of v dot dl along this particular line element would be 0. If Vr was non-zero in this case, then it would have had a non-zero circulation, but since Vr is also 0 and v theta is perpendicular to BC, that's why we have uh, the net circulation, that is V dot dl along BC is equal to 0. Okay. Similarly, now since we are considering CD, again we will consider the velocity component to be along this direction, right, along this curve. So since now the velocity is along the counterclockwise direction, then that's why it would be positive, contrary to what was that in the case of AB. So we will have the velocity component as omega r plus dr, right? So radial distance now is r plus dr, so the angular velocity would be omega r plus dr, because see here r is not a constant but a variable depending on the radial distance from the origin. So that's why since the radial distance from the origin here is r plus dr, so the angular velocity will also change accordingly. So we would have the angular velocity as omega r plus dr, and the arc length would again change, would be equal to r plus dr d theta. Okay, and similarly the circulation along d would be 0. Why? Because the radial component is 0 and the angular component is perpendicular to the line element. That's why the net circulation or the net product of v dot dl will be equal to 0. Okay, so we get that the net circulation the net circulation gamma of, that is the line integral of v dot dl, would be equal to just the sum of gamma AB plus gamma CD, because gamma BC and DA are 0. That's why you just need to add up gamma AB and gamma CD. So from that we get that gamma is equal to 2 omega r dr d theta. Okay, and again from the definition of vorticity, we know that vorticity is equal to circulation divided by area, right, from this expression. If we do a similar step, to find out vorticity, we just need to divide the net circulation from the elemental area. So this area would be given by r dr d theta. Okay, it's basically again an approximation, because if we consider this to be the arc length r d theta and this to be as dr, then approximating this element as a square, then this small elemental area could be approximated to have an area of r dr d theta. Okay, so just divide the net circulation by r dr d theta to get that the net circulation in this particular line in this particular flow domain is given by 2 omega. Sorry, net vorticity in this particular line element is given by 2 omega. Okay, so I hope this was clear. And again similar calculations can be done for free vortex. It's again, so I will not go through that for the sake of saving time, but from that we get that if we try to evaluate the net circulation from the in the case of free vortex, we get that the net circulation is 0, which again implies that the net vorticity is also equal to 0 in the case of free vortex. Okay, or basically what it concludes that the free vortex is irrotational. Okay, but the forced vortex has a finite value of circulation, and that's why has a finite value for vorticity, and the vorticity in the case of a forced vortex is thus non-zero. Okay, so this is a very important conclusion, and the concept of free vortex and forced vortex are also very extensively used in potential flows, and in fact in the modeling of tornadoes, of how the flow behaves within the diameter of the tornado, and how the flow decays outside the diameter of the tornado. That's model using the concepts of forced vortex and free vortex, right? So very crucial. But for today's session, or for today's assignment, or today's understanding, the important takeaway from the concept of free vortex and forced vortex is that forced vortex is has a rotational flow and free vortex has irrotational flow. Okay, because the circulation is finite in the case of a forced vortex, and in the case of free vortex the circulation is itself 0, which implies vorticity to be 0. Okay, so so finally we have the final concept of velocity potential. So again, velocity potential is defined for is only defined for irrotational flows, but again can be applied for 3D as well. Okay, so it's not necessary, or it's not only limited to 2D flows or 2D incompressible flows, but the only constraint for defining the velocity potential is that the flow has to be irrotational. That is, the curl of the velocity field has to be 0. Okay, and from the very definition of the curl, we can obtain the expression for the velocity potential. That is, if the curl of the velocity field is 0, it's every element of its every component of the curl of the velocity field should be 0, right? So that would give us that dou v by dou x minus dou v by dou y equals 0, dou v by dou z minus dou w by dou x equals 0, and dou v by dou z minus dou w by dou y is equal to 0. Then if we define a function phi, that such as u is equal to dou phi by dou x, v is equal to dou phi by dou y, and z is equal to dou phi by dou z, from that we get that this definition of the velocity potential phi inherently satisfies these equations, and thus the definition of the velocity potential is given by these expressions. Okay, so sometimes students may think that the definition of stream function and velocity potential are like just randomly made or randomly phrased by mathematicians. Actually it's not. It's actually very inherent to the basic definitions or basic consideration that we do while defining the velocity potential or stream functions itself. Like from stream functions we say that a flow has to satisfy continuity and has to be 2D incompressible. So from that we use the incompressible continuity, the approximation incompressible flow and thus tell that if a flow satisfies the continuity equation, it thus should have a stream function, and since the flow also has to be 2D, so it will only have two velocity components, and thus from those logic we define or derive the functional form or relation between the velocity components and the stream function. Similarly, in the case of velocity potential, we tell that since the vorticity is 0, then each and every component of the velocity field has to be 0. So from those equations or those definition, we are able to phrase the expression for the velocity potential and find a relation between the velocity potential and the velocity components. Okay, so I hope that's all for the discussion part. And again, one more important conclusion that we get from velocity potential and velocity and the stream function is that the lines with constant psi and constant phi, that is the lines of constant stream functions having constant value of stream functions and constant value of velocity potentials, are perpendicular to each other except at the stagnation points. Okay, and by the stagnation points I try to imply that the velocity at those points are 0, but it's both u and v is 0 at those stagnation points. Okay, so the definition is that the lines of constant psi and the lines of constant phi, where psi and phi denotes the stream function and the velocity potential respectively, are perpendicular to each other throughout the flow domain except at the stagnation points. Okay, so again, one more important conclusion or a special case for both the stream functions and the velocity potential are given by these expressions. Okay, so we have that u is equal to dou phi by dou x and v equal to dou phi by dou y. So for continuity equation we have that dou v by dou x plus dou v by dou y is equal to 0, and it would basically imply that the flow is incompressible. So if the flow is incompressible and irrotational, then the velocity potential must satisfy the continuity equation, right? So from that, if we substitute the value of u and v in this expression, we get that dou square phi plus dou square phi by dou x square plus dou square phi by dou y square is equal to 0. That basically tells us that the Laplacian of the velocity potential is 0 in the case of a 2D incompressible irrotational flow. Okay, similarly in the case of stream functions, we know that u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. If the flow is irrotational, like by very definition, for stream functions to exist, the flow has to be 2D and incompressible. But if we add on another constraint of having a irrotational flow, then it must satisfy this expression, right? That the z component of velocity field of the vorticity field has to be 0. That is dou u by dou y minus dou u by dou x equal to 0. And if we substitute this value of the velocity fields in this expression, we get that dou square psi by dou x square plus dou square psi by dou y square is equal to 0, or the Laplacian of the stream function is equal to 0. And these equations, or this satisfaction of the Laplacian by both the stream function and the velocity potential is very crucial when we will discuss the potential flow in this course. Okay, if at all we are discussing potential flow, the satisfaction of the Laplacian by both the stream function and the velocity potential is very crucial for the analytical solutions of the potential flow that we derive using the appropriate boundary conditions. Okay. And again, the final conclusion that we get is that even though for a 2D incompressible irrotational flow, since both psi and phi satisfy the Laplace equation, even though if both psi and phi satisfy the Laplace equation, it does not mean that the solution for psi and phi are the same. Why? Because the respective boundary conditions for psi and phi would be different. So even though if the governing equations are the same, there is basically a Laplacian of both psi and phi are 0. This basically implies that the governing equation for psi and phi are same. But since the respective boundary conditions on psi and phi will be different, that's why the solution of psi and phi are different. Okay. So that's the important takeaway from today's discussion. So let us now briefly discuss some problems, very simple problems. So let us go directly to the problems. So I hope it was clear till now. Okay, till now, right? For today's session.
Yes, please proceed.
Okay, so thank you. So I hope it was clear, and I hope you were able to grasp the concept or revise the concept as was discussed in the lectures by Professor Chakraborty. So I discussed extensively because today's problems are very simple and actually one-line answer type questions. So let us just dive to the questions immediately, and you will see why I am saying that. Okay, very simple one-line answers, and I hope you help me to find the solutions. Okay, so the first question is very simple again. An infinitesimally small fluid element as shown in the figure is subjected to velocity fields u is equal to kx plus y, v is equal to minus kx plus y, and w is equal to 0. Okay, so from this expression you can clearly see that the flow is 2D. Okay, 2D flow. Okay, because the z component of velocity field is 0. Okay, so the first question is let me zoom out a bit more. Okay, so the first question is determine the linear strain rate along the x direction. Okay, so it basically means that you need to find epsilon dot x, that is equal to dou u by dou x. Okay, so let me try to discuss this. It's again very simple, no issue. So we are given that u is equal to k x plus y. Okay, so the linear state of the linear strain rate along the x direction is simply would be given by dou u by dou x. Okay, it is this. So then again from here we can clearly see that if we take the partial derivative of u along the x direction, we will get that E dot x or dou by dou x is equal to k. So the correct answer for this question will be given by A. Okay, it's quite simple. Similarly, the linear strain along the y direction will be simply given by dou v by dou y. Again, just take the partial derivative of v along the y direction to get that dou v by dou y is equal to minus k. Okay, so the answer would be B. Again, we are asked to determine the rate of change of angle of line AB. Okay, so for line AB, as we discussed in today's session, that if this is the fluid element and this is the the deformation of the fluid element after some time delta t, A, B, say B dash, C dash, D dash, D, C. Then if this is alpha, this is beta, then alpha dot was given by dou v by dou x and beta dot was given by dou v by dou y, right? So if we just substitute the expression for v in this expression and take the partial derivative along the x direction, we will get that the rate of change of the line AB would be given by minus k. Okay, so dou by dou x of minus k x plus y, it will give us minus k. Similarly, the rate of change of angle AD, this line AD would be given by beta dot, which is dou u by dou y. Then partial derivative of dou by dou y of k x plus y would be equal to k, right? So the answer would be B. Okay, so again the question is determine the angular velocity of the fluid element. Okay, again we recall that the angular velocity, say z, would be given by half alpha dot minus beta dot. So it would be half alpha dot is minus k, beta dot is k, so it is minus 2k by 2 will be equal to minus k. Okay, so the answer would be C. And we are asked to determine a stream function for this problem. So since again it's very simple, I will just show you how to do it. Say for stream function we would have that u is equal to dou psi by dou y would be equal to k x plus y, right? V would be equal to minus dou psi by dou x would be equal to minus k x plus y. Okay, so once we do the integration for both these components, we will get that. Let us go to the derivations that I did. So from that you will get that here, yes. So from here you will get that psi is kxy plus ky square plus some function of x. Okay, once you do this integration. Okay, similarly once you do this integration, you will get that psi is equal to kx square plus kxy plus some function of y. Okay, and in order to find the expression for psi, we need to compare both these expressions, right, that we previously did. So from that we get that psi xy is equal to k x square plus y square plus sorry, it's actually k by 2 if I'm not wrong. So I'm sorry for the confusion. I'm sorry, it would be k by 2 times x square plus y square plus 2xy. Okay, again if you just consider that psi xy is equal to 0, right, then we get that x square plus y square plus 2xy is equal to 0. Okay, it's just actually from the expression itself, from the final expression, this you can just consider that the generic form of the stream function for different values of the constants would be x square plus y square plus 2xy, and just try to find the similar related expression in the options to get that the expression for stream function will be given by C, that is equal to x square plus 2xy plus y square. Like for a case if the constant that we are considering k by 2 is equal to 0, then we will have psi xy is x square plus 2xy plus y square will be equal to 0. Okay, it's just the value of the constant that determines different stream functions. So we need to capture out the generic term, which in this case would be x square plus y square plus 2xy. Okay, so this is the answer. And okay, the next question is quite interesting actually. Okay, so we have our velocity field as, say, u is equal, let me just write it. Okay, u is equal to kx plus y and v is equal to minus kx plus y, right? And the question is that which among the following figures correctly represent the shape of the fluid element subjected to a given flow field if k is less than 0, and we are told that k is less than 0. Okay, so in order to answer this question or answer this very interesting question, we need to actually look back and see the value of all the terminal or all the parameters that we have evaluated till now. So let us look into the deformation along the linear deformation along the x direction, that is equal to k, and if k is less than 0 then it is equal to negative, right? If k is less than 0, then dou v by dou y, let me write it as e dot x e dot y so that you are not confused, then we get that is equal to minus k, then it is equal to positive if k is less than 0, right? Let me just write it, because negative would make it positive, so e dot y is positive. Okay, then along the say alpha dot is dou v by dou y, which will again give us minus k, but again it will be positive is if k is less than 0. Similarly, beta dot is equal to dou u by dou y, which would be equal to k, but which would be negative if k is less than 0. Okay, now look at these expressions and tell me like which would be the most suitable deformed shape of the fluid element after some time, say delta t, where delta t tends to 0, because these expressions that we derived are only valid for the time delta t where the limit delta t tends to 0. Okay, so keeping those considerations in our mind, since we are getting epsilon dot x, it is linear deformation along the x direction as negative, negative, so it will basically mean that the fluid element has contracted along the x direction. Okay, so since initially our fluid element was square shaped, then since there is a contraction in the x direction, so this diagram among all the diagrams, these two diagrams seemed more suitable because there is a contraction along the x direction. Okay, so the correct option may be between these two diagrams. Okay, similarly, since epsilon dot y is positive, then the flow should elongate along the y direction, then again these two diagrams are suitable because the fluid element is elongated along the y direction. Okay, again alpha dot is positive, it basically mean that considering the notation used by Professor Chakraborty and the general trend of notation, we get that alpha dot is positive. It basically means that a fluid element will rotate along the positive along the counterclockwise direction. So this is correct. And similarly, we just need to check if beta dot is okay, so so and since you can see here that if beta dot is equal to, let me just check back. Okay, this is contrary to what I was thinking, so just check back to the conclusion that okay. So yes, I'm sorry for the confusion, so just okay. So if we try to find the net angular velocity of the fluid element, say omega z, it would be half of alpha dot minus beta dot, right? I'm just getting confused, so I'm sorry for the confusion caused. So let me just try to now answer it properly. Then it would be half of alpha dot is negative, so it will be minus k, and beta dot is positive k, so it will be minus k, so it will give us minus k, right? And since k is less than 0, it would basically imply a counterclockwise rotation, right? So the only diagram that satisfies all these conditions is given by diagram A, so the correct answer would be A. Okay, I'm sorry that I was getting a bit confused in these two notations. I was not finding the angular velocity of the entire fluid element, rather than I was just finding angular displacement of the individual line elements. So I'm sorry for this confusion caused, but the ideal way would be to find the angular velocity of the fluid element first, and if it is giving a constant value, then it basically tells us that there is a angular deformation along that particular direction, okay, or which direction sense the rotation is being considered. Okay, if it is negative, then it is clockwise. It is positive, then it is counterclockwise, and it is positive because k is less than 0 and it's minus k, then it will basically add up to get a counterclockwise rotation. Okay, there is along this direction. Okay, then the final two questions are again conceptual based. Then the question is, which among the following statements is or correct regarding stream functions and velocity potential? Okay, first statement is velocity potential exists for 2D incompressible flow. 2D compressible flow, that is not correct. Stream functions exist for 2D incompressible flow, then it is correct, so we'll tick that. Velocity potential function exists for rotational flows, that is incorrect. Then velocity potential function exists for irrotational flow, that would be correct, so B and D would be the correct answer. Okay, then the final question is, which among the following statements is or are correct regarding free and forced vortex? Okay, so this I guess I just discussed before starting the questions for today's session. So the questions are that in the case of free vortex, the circulation is 0, so that would be correct, right? So in the case of free vortex, circulation is non-zero, so that is not correct because we found that circulation is 0 in the case of free vortex. Okay, and in the case of forced vortex, circulation is non-zero, then again this is correct because we found that the circulation had a finite value in the case of a forced vortex. That was specifically 2 omega for our current for the problem that we encountered, so it was 2 omega in the case of a forced vortex. In the case of forced vortex, the circulation is 0, so this is again incorrect, so the correct answers are A and C. Okay, so I hope that's all from today's session. I hope it was able to help you to understand the concepts that were discussed by Professor Chakraborty in the lectures for week 6, which effectively gave us a brief overview or understanding of fluid kinematics. And I guess from the next week we will start the fluid dynamics part. But again, knowing the fluid kinematics is also very essential because it lays a proper foundation for understanding or to build up the concepts for the fluid dynamics part. Okay, so I hope it was clear. If you have any doubt, you can again please go back to the lectures by Professor Chakraborty or just put your doubts in the discussion forum. Okay, so I hope that's clear. Then I hope there is no doubt. Okay. Okay then. So thank you and have a nice evening. Okay. Thank you from. So and you can leave the session. So it's fine. Thank you.